So today, going to look at solving two variable linear systems. So solving systems of equations. Just to kind of break down that title, if it is a system of something, does that mean there's just one thing or more than one things? If it's a system, more than one thing. And if it's a system of equations, that means you have a problem with more than one equation. Okay? So, kind of looking at this first one, we're just going to build the equations here. It says, the admission fee at a small fair is $5.50 for children, $8.50 for adults. Last Saturday, the fair sold 2,200 tickets for a total revenue of $13,900. Next year, they plan to adjust the types of games and rides based on attendance. What was the mix of attendees, children's versus adults? Set up a system of linear equations to solve the problem. We won't actually solve this one. It says use the variable C for children, A for adults. So, a couple things before we actually get into this, and just a rule of thumb. By a raise of hands, who prefers, well, I'll put it this way. Instead of using C and A on this problem, how many of you would prefer to use X and Y? Okay. And usually it's about a 50-50 split. Some people like to use the variables that it's obvious what they are. C is children, because children starts with C. A is adults. If you're not one of those people, a lot of people just like working with X and Y. If you're one of those people on these kind of problems, you need to go off to the side and write that right there. Now on this one, because it says to use C and A, I'm going to use C and A. But if you want to use X and Y, that needs to be next to this problem on your notes. Right, it does not matter to me which way you do it. I can figure it out either way. So going back up to it, can anybody tell me one of the equations that would go into this system?
It'll be 550.
Okay, so 550. So there's 550 for each children, 850 for each adults. And total they made 13,900. So what would that equation look like?
550 plus 8.
Okay, go right here.
13,900 equals, and then 550 C plus 850, right?
Okay. So instead of 50, I'm just going to put 5.5 and 8.5. It's the same thing. Somebody else tell me the other equation. Well, what would that other equation be, do you think?
I'm not sure. It'll probably be X plus Y equals something.
Okay. Let's go back to what the variables stand for. I know I put children and adults. What exactly about children and adults? Is it their shoe size, or their height, or their weight, or their favorite color? Or do what?
Tickets, the amount the tickets are.
Oh, okay. What do you?
I think I got it.
How many? Okay. So how many tickets sold? So the number of kids and the number of adults, right? So let's make sure that we know that whenever I put children and adults, we're talking about the number of each kind. Okay. So it's L, correct?
Yes.
Okay. So the equation would be
C plus A plus 2.
C plus A equals 2,200. All right, you add up all the children, you add up all the adults. It told us right there that the fair sold 2,200 tickets. Okay, they don't sell tickets to dogs or cats or mice or anything like that. It's children and adults. And they're 2,200 sold. So it's some combination of children and adult tickets. So again, we're not going to actually solve this, but looking at this, This is a very common kind of system, to the point where I actually have labeled the kind of equations that you have. So this one is what I will refer to. And if this helps you, then awesome. If not, then sorry for wasting your time. This is what I call the value equation. The value of the child's ticket is $5.50. The value of the adults is $8.50. The value of all the tickets is $13,900. In your value equation, you're always going to put the value of whatever that is in front of that variable. So you're going to have coefficients here. All right. Another common question is, let's say I tell you in my hand I only have nickels and dimes, and it adds up to $5.10. So you would put the value of a nickel in front of the variable n, the value of a dime in front of the variable d, and set it equal to the total value, which is $5.10. Every number in there represents a value somehow. The second equation is what I call the number of. And this is where you're just going to add up this variable plus this variable, and then equals the total number of whatever it is. Okay? So children plus adults is 2,200. Going back to the nickels and dimes thing, let's say I had 15 coins in my hand. So you would put n plus d equals 15. All the nickels plus all the dimes equals 15 coins. Okay, so not all of your systems are going to be set up with those two kind of equations, with that mindset. A lot of them are, though. All right. So let's go to those graphs down below where it says case 1, case 2, case 3. It says 3 different 2-variable systems of equations are depicted below. What is the solution for each case? And explain. So first, looking at a graph, where is the solution found? The solution is where the lines cross. Or intersect is probably a better word for that. So, looking at case 1, what is the solution there? Negative 2, 1. Situation 2, what is that? No solution. Okay, if the solution is where they cross, well, if they never intersect each other, then there's no solution. Case 3, it's kind of hard to see, but if 2 lines are right on top of each other, infinite number of solutions. So we're not going to talk about the graph a whole lot today, but whenever you're looking at a graph and you're solving a system, that's what you're looking for. Where do they cross? If they don't even cross, if it ends up being the exact same line sitting right on top of each other. So let's go to these 2 different methods right here. If I raise a hand, how many of you remember the words substitution and elimination from Algebra 1? Awesome. Okay. The majority of you remember it. Those who don't just have a bad memory, because I know it's taught. So on the first one, if I have substitution, if I already have a variable that is given, y is already solved for, I can take 2x and I'm going to plug it in for y into the second equation. So I'm going to end up with x plus, Okay, instead of y there, I'm going to put 2x equals 12. And then Alex, what would I do from there to solve? And that would give me what? 3x equals 12. And then Preston, what is x going to equal?
4.
Am I done with this problem?
No.
What do I need to do?
Plug in for x. Plus x1.
So am I going to, which one, or does it matter which equation I plug this into?
Yes.
If it's a system, it won't matter. I'm going to plug the one into, in my mind, the one that's easiest, which would be the first one. So I'm going to do y equals 2 times 4. 2 times 4 is 8. I'm okay with you giving your answer like that, but don't freak out if it's some kind of multiple choice thing. A lot of times it would be given as a point. Going over to elimination. If you've forgotten, whenever I do elimination, I'm going to look at this problem, and it needs to be in standard form. X is on top of X's, Y is on top of Y's, and so on. And I'm going to look at each column as if it's just an old, elementary, easy mathematical problem set up vertically like that. Okay? So on my X's, because this is positive 3, I would do 5x plus 3x, which is 8x. And then what is negative 6y plus 6y?
0.
0. So those cancel. They are eliminated, hence the name. All right, and that's kind of the idea behind elimination. Negative 32 minus 48 is going to give me negative 80. So x equals what? Negative 10. Again, does it matter which equation I plug it into? No. So I'm just going to do the second one. So I've got 3 times negative 10 plus 6y equals 48.
It should be negative 48.
Yes, negative 48. Thank you. So I'd multiply to get negative 30. I would add 30. And then I would divide by 6, divide by 6. If you look up there, a question that I had last class, somebody asked me, how do I know, whenever I'm doing these problems like this, how do I know whether to add or subtract? It all depends on what the sign is on the bottom number. Okay, that 48, it's negative. So I'm going to do negative 32 minus 48. This 6y is positive, so negative 6y plus 6y. 5x plus 3x, because that 3x is positive. So if you look at those questions, and I'm going to pop the work back up on the screen here while we answer them, so I can refer back to them if I need to. Just a second. There it is. And both these questions, they're kind of asking the same thing. I don't know if we necessarily need to answer both. But on 3 it says, what was different between the problems for substitution and elimination in the above example? So, yeah, what was different about them? Nick Miller. Just kind of look at
For one, you substituted one.
that. Well, that's correct. So about the substitution problem, what's different about the way it was given versus the way the elimination problem was given?
The substitution, one problem is like already, or what? Not one problem. One variable is already solved.
There you go. So for substitution, a variable is already solved for. Something else I would notice about the substitution problem is that it has coefficients of 1. Ethan, what do I mean when I say coefficients? What is a coefficient?
So it's like how much of a variable you have. Like 2x. So the coefficient would be 2, wouldn't it?
Okay. So it's the number in front of the variable. So if you look at the substitution, you've got x plus y, so that would be 1x plus 1y, y equals 12, and then the y up top only has a coefficient of 1. For elimination, what's different about the elimination than substitution?
You're getting rid of something.
Do what?
You're getting rid of something.
Okay, within the process I'm getting rid of something, but just with what's given there.
You have to solve for both.
Well, let's just solve.
It has negative.
Well, they both could possibly have negative, and in both problems we're solving for both x and y. Philip, I think you're kind of getting towards the right direction though with your answer. What do all the variables have? Coefficients. So has coefficients not equal to 1. The other thing that I would recognize about a problem is, in order for me to use elimination, does a variable cancel through subtraction? Okay, we had the 6y minus 6y. So a lot of the answers on this next question is going to come from these answers. You don't necessarily need to write anything down. I'm just going to talk about it a little bit. It says, what criteria would you use to choose substitution or elimination? How do you decide? And eventually you're going to kind of lean one way or the other. And this is one of those things where it's normally about a 50-50 split that people like substitution or elimination. If I have a variable that's by itself, no coefficient, I'm going to use substitution 100% of the time. All right? I'm normally only going to use elimination if this situation is there. A variable obviously cancels out. It does make the problem shorter if that's already there. Sometimes you'll have to change one of the equations if you use elimination. Okay? And then we'll see one. I'll talk about one like that here in just a minute. Okay? So you need to kind of look. I would recommend that you look to see, depending on what's given, which method is going to be easier for you. All right? If they're about equal, you're going to lean one way or the other. I don't care which way you go. Okay? So right here, I'm going to do one of these problems. We're going to do one of them together, then I'm going to talk about the rest. We're going to do one word problem, and you're going to do the extra practice on there. So looking at, let's just go to 5. So would 5 be easier using substitution or elimination? Why substitution? Because I've got a variable that's already solved for. Okay, now this one looks weird because it's the equation then equals a, but I can do the same thing. I'm going to take 3b minus 20, and I'm going to plug it in right there for a. So because it starts off with that, I've got 3b minus 20 plus b equals 12. After that, I'm going to need to simplify that to solve for b. Lyndon, what would you do first on that problem?
I guess add the 20.
Okay, I'm going to add 20 to both sides. So I've got 3b plus b equals 32. Bryce, what would I do after that?
Combine the B's.
Combine the b's. And so, Will, what does the b value equal? Am I done with the problem? No. One reason I like substitution is whenever you have to find the second variable, even if I had to do work to get here, let's say the original equation was this, and I just subtracted 20 over to get that, then I have an equation that's already set up for me to just plug it in and figure it out. I don't have to move stuff around. So I'm going to have a equals 3, instead of b I'm putting 8 in there, minus 20. 3 times 8 is 24. 24 minus 20 is 4.
Did you also use the second? Okay.
Alright, so just going through the rest of these, on 6, is 6 set up to do substitution or elimination? Sub x equals, so substitution. I'm going to talk about 7 here in a minute. What about 8? Elimination. Why elimination? Has no variable by itself, and you've got minus y plus y. 9.
Elimination.
Same reason. Negative 3n plus 3n. Let's look up at 7. How would I do 7? What was the answer? Is it you saying that?
You can multiply the bottom by 3 so that 3x and
Okay, you could do that. There's a little bit easier way. How else could I do that one? Do I have a variable solved for? Yes, right? In both equations, right? It's y equals in both. So it is substitution. It just looks weird. If I know y equals 3x minus 2, and y also equals negative x minus 6, I can substitute 3x minus 2 in for y. Okay, and let me kind of give you an example of this. Does $1, so look up here. Does $1 equal 4 quarters? Yes. Does $1 equal 10 dimes? Yes. So does 4 quarters equal 10 dimes? Yeah, it's all the same, right? It's all $1. It's just broken up differently. Same idea here. $1 equals 4 quarters. $1 equals 10 dimes. So 4 quarters is the same as 10 dimes. And you would solve it from there. Alright? There's another way that you could do it, and I'm not going to get too much into it. But if they're both set up as y equals, you can put both into your calculator, y1, y2. And if you remember the little trick on how to find the intersection on the graph, you can also find it there. Okay, so I'll let you see if you can retrace your memory back from when you were taught that. Looking at number 10. Going to do, okay, so I've got, it says you have 14 coins and nickels and dimes. So kind of what I was talking about earlier. It says if your coins total $1, how many of each do you have? Okay, so L, on these kind of problems, would you rather use N and D or X and Y? X and Y, okay. So I'm going to do X and Y. If you would rather use N and D, that is fine. But because I'm using X and Y, I'm going to do nickels and dimes. So can somebody tell me, and think about kind of the value equation and then also your number of equation. Can somebody tell me what one of those equations would be?
X plus y equals 14.
Okay, there's my number of. Just the number of nickels plus the number of dimes equals 14. Can somebody tell me the value equation? Philip.
5x plus 10y equals $1.
Okay. L. We'll get something different here. Or it's not L, sorry. No L.
So 0.05n plus 0.1d equals $1.
Okay, so now listen, no L is 100% completely correct, but don't write it. I'm going to write what she said up there, but then I'm going to show you something else on this. So don't write what I'm about to put up here. So she said 0.0, and no, correct me if I do any of this wrong, 0.05x plus 0.1y. If you put 0.10y, that's fine. A lot of people like to do that because they can see the 10 cents for the dollar, whatever. Okay, so I'm going to leave it like that, and then that equals $1. Okay, 100% correct. But on this kind of problem, the way I would do it would be that right there. Okay, and Philip, you might have been getting at this, maybe not. So, by a raise of hand, how many of you think this equation looks easier to deal with than this equation? Right? No decimals. Because you start subtracting decimals, now you're dealing with, if I got to subtract that, that's going to give me 0.95, that's going to give me 0.9, and it's just going to start to kind of be a little bit of a pain. On these kind of problems, and these are pretty common, the coin problems, instead of thinking out of $1, if you think how many pennies is that worth, you don't have to deal with the decimals. So if I'm looking at that, every nickel, there's 5 pennies in every nickel. There's 10 pennies in every dime. Just make sure that you're careful that you got to do the dollar as well. There's 100 pennies in $1. So looking at this problem, does this one looks like it would be easier using substitution or elimination? Or is it kind of half and half? Do what? Okay, elimination. Elimination. Okay, so I'm going to do elimination. Me personally, I would do substitution because both of these have coefficients of 1. I could subtract x, I would have 14 minus x, and then I would plug that in for y. But I told you earlier I wanted to talk about a problem where we would change one of the equations so that we could do elimination. So let's do this right here. Right now, do my x's eliminate? No. X plus 5x would give me 6x. What about my y's? No, that'd give me 11y. So I'm going to look at this. Let's try to eliminate the x's. If my bottom one is 5x, what would my top term need to be? Do what? Well, negative 5x. So I've got to multiply that whole equation by negative 5. That's going to give me negative 5x. It's going to give me negative 5y. And it's going to give me negative 70. Now I can do the elimination process. My 5's cancel. 10 minus 5 is 5. 100 minus 70 is 30. So that tells me that I have 6 dimes. Whenever you're solving, I would always refer back to, I say always because I didn't earlier on one of the problems, and I think it was L corrected me over there. I would always go back to the number of equation. So I need to find x. What plus 6 equals 14? 8. So I would have 8 nickels.